Let's remind ourselves how collisions work. We go back to the days when we used bus topologies on Ethernet networks, maybe 10 base 2, maybe 10 base 5 technologies, and the devices attached to this shared segment had to make sure that there was not currently a frame on that shared segment before they transmitted. We're not allowed to have more than one frame on a shared segment at any one time. And remember that they could use a technique called CSMACD. Carrier sense multiple access with collision detection. Carrier sense meaning that they can determine that they are attached to the network and they can listen to the network to see if a frame is present on the shared segment. Multiple access means that we don't have to take turns. We can have multiple devices accessing the same segment, and when it's clear to transmit for anybody, they can transmit. And collision detection, the CD in CSMACD, means that if a collision does occur, if we do have two stations that transmit at the same time and those transmissions collide, we can detect that and we can retransmit. Here's a challenge that can occur on a shared segment. Let's say that we had a couple of stations, maybe the two bottom stations on screen, they were simultaneously listening to the wire to see if it was okay to transmit, and they heard the same period of silence. They independently concluded that it was okay to transmit, so they both transmit at the same time. And what happens? They collide. We had a collision that occurs. Something that's often misunderstood about collisions, by the way. You might guess that as soon as a collision is detected, the remainder of the frame would not be transmitted. The PC would say, "Oh no, my frame collided with another frame. Let me stop." Actually, that device will continue sending that frame. The idea is we want to make sure that everybody on the shared segment knows that a collision occurred. And if we stop transmitting immediately as soon as we detect a collision, other devices might not know. So we continue to transmit that frame. That process, by the way, is known as jamming. Jamming is continuing to transmit a frame for a short time so that other devices on a shared segment can know that a collision did occur. And after the collision occurs, the devices that sent the colliding frames, they obviously need to retransmit those frames, but they don't want a collision to happen again. So what they will do, they will independently set a random back-off timer. Just as an example, let's pretend that the device on the bottom left set a random back-off timer of 10 milliseconds, and the device on the bottom right set a random back-off timer of 20 milliseconds, and then when they retransmit after these random amounts of time, they're less likely to collide again. That's the way that CSMACD can help support multiple devices on the same shared segment. Today, though, we almost never use a physical bus topology like we have here. In fact, we've also largely gotten away from Ethernet hubs. But if you do run into an Ethernet hub, it's important to understand that all of the ports on an Ethernet hub, they're in the same collision domain. Meaning that even though we're physically connected in a star topology, logically it's still a bus. It's still an Ethernet bus where there can only be one frame on this shared segment at any one time. We've got one collision domain. Remember how a hub operates. A hub does not make intelligent forwarding decisions. It just takes bits that it receives in on one port and sends them out other ports. This can limit scalability. If we have lots of devices on the same shared segment, they're going to be able to transmit less frequently. To increase our scalability, we could replace that hub, as most people have, with an Ethernet switch. In the example on screen, I have 4 devices connected to this Ethernet switch, and as a result, I've got 4 collision domains. Each port on an Ethernet switch represents its own collision domain. And because we only have the one device on a switch port, that means that we don't even need to run CSMACD. This is a big deal. If I don't have to run CSMACD because there is no possibility of collision, that means that these stations connected to an Ethernet switch, they can run in full duplex mode as opposed to half duplex mode. In full duplex mode, that means that I can have a station that is simultaneously transmitting and receiving. If we had a hub, and if we had to run CSMACD, a requirement is we have to run in half duplex mode. This means that an Ethernet switch not only helps us scale our networks by helping us out with the collision issue, but it gives us a more effective use of our bandwidth. We can now use full duplex as opposed to half duplex communication. We know that an Ethernet hub has all of its ports in the same collision domain. In other words, a collision that occurs off of one port affects everyone. Let's contrast a collision domain with a broadcast domain. A broadcast domain defines how far a broadcast is going to radiate throughout the network. If we look at the layer 2 MAC address of a broadcast frame, the destination MAC address is all Fs, and there is no device on the network that would have a network interface card with a MAC address of all Fs. This means that a switch, it would never learn the all Fs MAC address. And what does a switch do with an unknown destination MAC address? It floods it. It sends that frame out of all of the other switch ports other than the port that the frame was received on. And to get back to our Ethernet hub, just as all of the ports on an Ethernet hub belong to the same collision domain, they also belong to the same broadcast domain. A broadcast seen on one port will be sent to all other ports on an Ethernet hub. What about a switch, though? We said with a switch, an Ethernet switch, every port was in its own collision domain. What about broadcasts, though? Well, remember, we just said that a switch will never learn the all Fs MAC address, and as a result, when it receives a frame in on one port destined for an all Fs MAC address, a broadcast frame, it's going to flood that out all of the other switch ports other than the port that the frame was received on. This means that all of our Ethernet switch ports belong to the same broadcast domain. This could start to impact the scalability of our network if we had a very large network and we had a lot of broadcast traffic. So the big question is, what will separate a broadcast domain? A hub doesn't separate broadcast domains. Switches don't separate broadcast domains. What does? A router. A router is a layer 3 device. It's the network layer of the OSI model, and a router will separate broadcast domains. Broadcast traffic seen off of one router port will not be seen off of the other router port. In other words, the router is not going to forward that broadcast traffic. As a result, a layer 3 device like a router, or even a multi-layer switch, a switch that can do routing, a layer 3 device like that, it can separate our network into different broadcast domains. Let's do a quick summary of what we've now said. We said that all of the ports on a hub belong to the same collision domain and to the same broadcast domain. We said that each port on an Ethernet switch belongs to a separate collision domain, but they all belong to the same broadcast domain. We said that a router could separate broadcast domains. This means that every port on a router could belong to a different broadcast domain, and of course, each port on a router also belongs to a different collision domain. As we consider a modern-day switch, let's think back to the 1980s. Back in the 1980s, that's when Ethernet bridges came out. Back in the 80s, networks were relatively slow. Implementations of Ethernet were 10-base-2 or 10-base-5 typically, and bridges were developed to limit collision domains. This allowed networks to scale somewhat. You could have a collection of hubs on either side of a 2-port bridge, as an example, and collisions seen on one side would not impact traffic on the other side. Architecturally, bridges worked a lot like computers of the day. If you had a Unix workstation, it might be using a RISC processor, or you might be using a computer that had a CISC processor. CISC, by the way, is complex instruction set computing. RISC is reduced instruction set computing. The bottom line is, frame forwarding decisions were made in software, and as a result, this frame forwarding was relatively slow compared to what we have today. The big change came in the 1990s with the introduction of switches. And on screen we see the Cisco Catalyst 3750 series of switches. In the 1990s, even though these particular switches were not available in the 1990s. But in the 1990s, with the introduction of switches, we started to have relatively fast networks. I personally remember different vendors coming into my office and explaining how architecturally their model of switch was better than a competitor's model of switch. And we had all kinds of discussions about interframe gap times and how frames were forwarded. But in reality, they all approached wire speed. They were all very, very fast. And that was largely due to having ASICs, application-specific integrated circuits, chips built into the Ethernet switch that made the frame forwarding decisions. No longer did we have to rely on a software program, essentially, running on a CISC or RISC processor. No, now we had dedicated circuitry that was in charge of making those forwarding decisions. And switches, like bridges, they limit collision domains. But one of the big advantages besides speed is, as you can see on screen, switches tend to have a much higher port density than bridges. You have a much lower cost per port when it comes to an Ethernet switch as compared to an Ethernet bridge. And the topic we want to discuss over our next few slides is frame forwarding. We've got different frame forwarding options. In other words, when a frame comes into one of those Ethernet switch ports, when does that switch begin to forward the frame out of the egress, out of the outgoing port? One approach we're going to discuss is cut-through switching. We're going to contrast that with store and forward switching. And a third type, which is really sort of a compromise between the two, is something called fragment-free switching. Let's begin our discussion with cut-through switching.